Johnny's sequence. It's going to start with a quick homing sequence where it hits the limit switch, moves off a certain amount, and then starts. Now at this point, I'm not going to touch any buttons. It's reached at 7 inches, had that 1 second delay before the press down, and now we're at the end. Each segment's super quick, 3 seconds, so I can't talk that fast. Now we're gonna let this one finish, and now we're gonna do a button press. Button press, it moves the 6.5 inches, moves, presses, and goes back. Same sequence. Missed it that time because 3 seconds goes by quick. Here we are. Here's the 6.5 inches again. Wait a second, press, and down. One more time. And
here we have the wiring diagram for our nip roller axis. This is using an internal amplification from the Galil and a sensor here acting as our registration mark sensor. Next we have the wiring diagram for our pressing axis. Here we have external amplification using the digiflex, and the digiflex is being programmed using a computer, and it sends a reference signal from 0 to 10 volts to the motor command on the Galil, which proportionally applies a current and torque to the motor to get it to the desired position. And here we have our limit switches for the stage. Here we have our calculations for the linear motion of each axis based on the rotational motion of each axis, and a couple of different calculations for different moves. And obviously down here, this takes into account the pitch of the ball screw of our stage. And in the very bottom, there are calculations for our half-second press at 30 newtons. And this is also shown in a later picture as 3 kilograms, which is proportionally 30 newtons, just to show that visual response. And then here are some flow and timing calculations we did, just general calculations to get our speeds and distances down to be under 3 seconds and to have a nice response. Here we have our driveware software connected to the motor using the digiflex. And here we have verified all of our motor parameters using the data sheet. And next, Andy will talk about the commutation.
so once we have done our tuning, which Lucas will cover later, the big thing for auto commutation is so we can make sure that the Hall sensors are configured to the correct phases. This is important so we can get the motor spin the right amount of times and start spinning with the right current at the right time in the right place. Moving back into tuning.
Here we have tuned the proportional constant and the integral constant for our current loop, which ensures we get a nice overdamped response for a step input on our motor.
This was important because we wanted to make sure the standard square wave matched what it was expected, and we were able to generate a nice, even, critically damped system.
Here we have our Galil design software where we have connected both of our motors. In here we have the tuning settings where we are tuning the P, I, and D constants. The P constant basically gives you an effort out based on the amount of air, proportional to the amount of air and this can be thought of as a spring, giving you more effort the more amount of air you have. The I constant essentially gets the steady state error to 0 as it looks at the error over time. The D constant basically adds damping to the system and prevents any spikes or drops in rapid spikes or drops in the air, potentially caused by sudden impacts to the system or sudden spikes in torque or current. Here we have our torque limits. Here is our continuous torque limit at 0.5 volt, corresponding to 30 newtons of force out from our pressing axis, and this was done simply to show a visible response rather than the 3 newtons of force, and a peak torque limit here of 1 volt, which would be twice the continuous torque limit.
Moving on to the drive settings, here are some of the parameters we used for our system. We had our speed of our axis C, which is our press axis, to be 221,950. We do this so we can move that 2 inches in half a second as we press it down, or in less than half a second. And our encoder takes that much of counts to rotate. Our acceleration for our A-axis is 12,000 and our C-axis is 500,000. Deceleration match, and the jog, which is also the jog over A, which is also the speed, is 4,300 counts. This correlates to our speed we need in order to reach that 6.5 inches in the required time. Also in this setup we have our CN, which is the limit switch configuration. We turn this to 1 so that the way these switches work, that way they'll be seen. LD is our limit switch disable, which if we have limit switches on, because we did CN1, we have to ignore the other limit switches because they're now opposite, and so we have to disable the other 3 axes. CE is configure the encoders on each motor. Each of them are using reverse quadrature, and so they need to go to 10. And lastly, the 2 motors are both servo 3-phase motors, and so we set the MTs to 1. And just a quick glimpse at our code. Here is Johnny's system, and we are running through it to get through. Just a quick overview on what this code actually is doing is the flow chart behind it is we are waiting for a button to press or for the counts to reach the 7 inches. After that, A moves the 6.5 inches, waits 1 second, and then our axis C, the press axis, starts to descend the 2 inches, the 69,000 counts. C moves a very minuscule amount to press down, hitting that 3 newtons of force we needed to seal it for half a second, and then moves up. Once it reaches a 1/2 inch up, A-axis will then start moving out, and then we start the whole process over again. Here we have the error calculations for each axis. As you can see, there are 4 different start-stops points, and this is done through the Johnny testing, both using the button switch and the 7-inch segments, and at the same point we got a good, very, very, very small error to the point where we're talking 2 counts of error, which was consistent every time we ran. Here is the actual data tracking that we use for testing.
Most of the limitations that were found during this application came from the inherent system response of both axes, including the motors and the connected components. This came down to the PID values that were used to tune these motors to the desired outcome given the input, and other limitations came from lack of experience with the hardware and software involved, mainly the Galil. The components used were not limiting factors, as high torques and Crazy high speeds were not required for this application. However, if low costs were important for this application, these components may become a problem.